Good morning, everybody. Can you hear me? Okay, so welcome to our third online session. Um, this is going to be, we're going to start talking about Newton's laws today. So, um, where can we find the live stream from yesterday? That'll be in the class playlist. So there's a link on Blackboard. I can put those links on Teams as well. It seems like we're using Teams for more stuff potentially. Um, So a couple administrative issues first. I'm sure everybody got the email about how we're out for the rest of the quarter. I imagine folks are thinking about that, and I guess it's a it's a really big disruption for class. But I would say the thing that comes to mind first is just I hope that you and your families and everybody are doing okay, and that you're not in danger or anything like that. And really, class is secondary to that. So I think we're going to be able to learn a lot, and as long as people are able to stay safe and everything, we'll be fine. Is the big picture. Okay. So, uh, in terms of administrative issues with class, with regards to the fact that we're going to be out for the rest of the quarter, I'm going to put some energy basically starting now into coming up with how we're going to do exams online. So expect us to do some sort of a practice trial run with this early next week, and then we'll try and do some kind of actual quiz at the end of next week, is my thinking. So this will give us time. It'll only be on stuff that you've completed homework on. You'll have, I'm not going to quiz you on anything where you have the homework still out, for example. Um, let's see. So yeah, I mean, obviously this isn't an ideal situation for a lot of the things that we want to do in class, but we're gonna get it figured out. It'll work out. Um, so yeah, we'll try a practice quiz, and then the other thing that's really impacted, especially, is lab. So I am pretty bummed that the Friday lab sections, we never actually had lab. So I've gotten a number of questions about that, and I've tried to get back to you about that. We'll talk tomorrow in our Teams session about what to do with the free fall lab. If you still, I suspect a fair number of students have questions about that. We'll work through that. We'll make sure that everybody's on the same page with the sample data. That lab is really important just because we use G for so many things that I don't want us to just not give that some attention. So we'll talk about that in Teams in addition to working with MATLAB. So the MATLAB won't take a ton of time, so we should have time for both. Um, so yeah, and then in terms of turning in the MATLAB graph, you can submit it as a PDF is fine. So you can export the figure itself as a PDF rather than a screenshot is probably the best practice. Um, Let's see. So yeah, bear with me, Friday groups. I'm sorry about the lab situation. That's not the best, but we'll get it figured out. I have some ideas. We're gonna need to get creative, right? Because we don't have access to our lab equipment, but you do have most everyone has in their smartphone a really sophisticated piece of data acquisition hardware. So if you haven't already, play around with Firefox. I'm right now I'm going to be coming up with uh, new things that we can do with that. One of the things that I think is really critical about lab, is to get experience taking and dealing with experimental data, manipulating experimental data. So I'm pretty averse to just giving you canned data. I want you to have the experience of messing with your own data, of being able to change things and see what happens to the data. So, and we can do that with Firefox, which is pretty cool. So stay tuned. Bear with me. We'll get some experiments figured out with that. Um, let's see. Uh, the other logistical issue. So the new homework for Chapter 4 has posted as well. So you should be able to access that. And we also pushed the date back for the other assignment that'll be due this evening. So Newton's laws. That's what we're going to talk about today. Does anybody have any questions? Yeah, what is it called? PhyPhox. PHYPHOX. Tell you what, I'll put that on the board for today. So one thing that I'm uh, gonna try and do is use OneNote. So with regards to being able to export our whiteboard screen, I think this will work better. I should be able to just make it into a OneNote document, and then everybody should be able to get access to that. So hopefully this will be an improvement over the whiteboard. I'll figure out how to post it, and then we can have that as a resource for everybody in addition to the video. So, okay. Newton's laws. Uh, I'll show you some slides first because there's some sort of text-based things, and I think it would be better to show you those typed rather than me drawing on the whiteboard with my less than ideal penmanship. So, Newton's laws. There are 3 Newton's laws. I suspect this is probably a subject that most folks have been exposed to. So I'm not going to go into, we're going to go through them all today and get started on working some example problems. But this, of course, is a subject that spans multiple chapters in your book. So starting with chapter 4. So start looking at chapter 4. So really, Newton's laws are basically, they're the meat and potatoes of mechanics. This is a big chunk of what we learn about in this class, PH2011. And this is a subject that engineers, mechanical engineers especially, need to know this stuff. You have to own this stuff. You're going to have subsequent classes, things like statics, dynamics, etc., that are built upon this. So you want to build up the skills now in our class, so then when you get to those classes, it's you don't have any holes in your understanding. So I just really want to emphasize that these topics may seem, some of them, if you've seen them before, might seem like, this seems pretty straightforward. Things like messing with vectors that we did yesterday. But it's all building on top of itself. So, and this subject is also one where we have a lot of notions about what these things mean. Things like force and mass and weight, and they may be sort of interchangeable, but really we want to take those kind of lay definitions, common understanding definitions, and give them instead a precise physics science definition. So that's part of our task with this too, is to sort of take our notions about these ideas and make them correct and concrete. Okay, so Newton's first law. So this, I'll state these as they're stated in your book for continuity, and then kind of give you a little bit of extra explanation. So Newton's first law states that every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. So this is basically an object will keep doing what it's doing unless there is some net force that acts on it, some total force. This is often called the law of inertia. And an object's inertia is given by its mass. And the unit of mass for our system, the metric system, is the kilogram. So what this means is an object is going to stay at rest, or it will continue moving in a straight line as long as no force acts on it. So this is hard to see in our common experience because there's always drag or friction or something that's slowing things down. But if you can imagine in outer space, for example, if you launch some object, it is going to continue in a straight line basically forever until it encounters some force, it runs into something, and that collision exerts a force and slows it down, or it experiences some gravitational force that grabs the object and changes its uh, state, it moving in a straight line. Another detail about this is you can have an object that's moving at constant speed, but that is not the same thing as constant velocity. Okay? So, in other words, if you're rotating, spinning in a circle, you are accelerating, and this does not apply. And we'll talk a lot more about this in the next chapter when we talk about circular motion. But it gets at one of these ideas that we talked about on the first day, the difference between vectors and scalars. So velocity is a vector, speed is a scalar. Spinning in a circle, you're changing direction, you're changing your velocity, even if you're not changing your speed. Okay, that's Newton's first law. Newton's second law gives us the mathematical underpinnings that we're going to use to solve many problems in this course. So let me state Newton's second law, and then we'll talk about it in mathematical terms. So the acceleration of an object is directly proportional to the net force acting on it, and it is inversely proportional to the object's mass. And the direction of that acceleration is in the direction of the net force acting on the object. So we've normally seen this as F equals ma, I suspect. I have this written as sigma F equals ma, and that's to alert you to the fact this is the sum of forces, the net force on an object equals its mass times its acceleration. And I've tried to be precise here by noting that both force and acceleration are vectors, so I have a little arrow on top of their symbols. Mass is not. Mass is a scalar. So, and then in terms of seeing how an acceleration depends on force and mass, it is directly proportional to the net force. So the bigger the force, the bigger the acceleration. And it's inversely proportional to the mass. So in other words, the more massive the object, the smaller its acceleration will be for a given force. Okay. So this gives us our relationship between force and acceleration, between mass and acceleration. So far, we've talked about kinematics. We talked about describing motion. Now we're talking about what causes it. So the thing that causes an acceleration is a force. Okay. Questions? Give me something in the chat window just so I can tell that we're on board. We're not having any technical issues. Cool, cool, cool. Questions? Okay. So I suspect most folks have seen this already, I imagine. So I'll ask you guys, have you seen this before? It's okay if you haven't. Not everybody has, but yeah, so yes, put in the chat if you've seen it before. And like I said, if you haven't, that's totally fine. Not everybody has had physics before. So that's part of why we I'm trying to emphasize, or maybe it's been a while, maybe you saw it a while ago, and now this is review. So my thinking is we'll go through this slowly the first time, just because I don't want to jump into something, and if you haven't seen it before, use terminology without defining it so that it's confusing. We'll kind of make sure we're all starting from the same place and then build. Okay, so a couple other notes about Newton's second law. I kind of already mentioned this, but the force, you can think of that as an action that's responsible for accelerating an object. It's the thing that's capable of accelerating an object. And we get to learn a new unit for this. So Newton's laws, he also earned the unit that we use for force. So a Newton has units of mass times acceleration. In other words, it has units of kilograms times meters per second squared. So that is the Newton. So if you're specifying a force, you would need both, generally, since it's a vector, you would need both its direction and also its unit, which will be the Newton. Okay. So, I want to emphasize net force. So I put in there, the sigma to indicate the total, the net. That's what they mean when they use that terminology. Haven't seen that before. So you can kind of see how this connects with our conversation yesterday. We looked at that in a fair amount of detail problem to find the sum of those two vectors. Well, the game with this is you need to add force vectors. If you find the force, the net force, you know how an object is going to accelerate because it will accelerate in the same direction as that net force, and that is proportional to that net force by its mass. Okay. So in other words, just to reemphasize, this Newton's second law gives us the connection between acceleration and force, describing motion and causing it. Okay. Newton's third law. Whenever one object exerts a force on a second object, the second exerts an equal force in the opposite direction on the first. So this is, sometimes we talk about this as like action and reaction force. One excellent example that you can think of this, just to kind of keep it at, to make it physical, you're probably looking at your computer or your phone or something. If it's resting on a table, you can think of the forces that are involved in this situation. So you're going to have the force of gravity that's pointing down. This is called the object's weight. And there's going to be a force that's in the equal and opposite direction exerted on that object, the computer, the coffee cup, whatever, that's pointing up, and that is called the normal force. And in this situation, when we say normal, we mean perpendicular to the surface force. And we'll look at this. I'll draw on the whiteboard for you. I can show you this in pictorial terms. And we will talk about some different scenarios today where the normal force, this perpendicular to the surface force, a lot of times it is the weight, but not always. That is not always the case. Okay. So one other thing I would emphasize with regards to Newton's third law is to think about this as an object in isolation. So you want to think about this as the forces acting on a single object, not the forces acting on, say, a collection of objects, or on some two objects together or something like that. You want to think of an object in isolation, and then that'll help us from getting confused about the application of Newton's third law. Okay, so that is Newton's three laws in a nutshell. I'll post, this is the kind of subject you can find tons and tons of excellent lecture and information about. It's such a, like I mentioned, it's such a sort of bread and butter topic to the point that it can almost be overwhelming. So I'll post some additional stuff in our playlist, but I have tried to sort of boil it down to um, the key points. I would also emphasize looking at chapter 4, read chapter 4 in your textbook. It talks about this in more detail. Um, so that's what Newton's laws are. Let's talk about how you use them. That's going to be much of what we're going to be doing in chapter 4 is basically building up um, the tools to solve different kinds of problems. So a question, is the slideshow going to be posted? Yeah, I'll put it on Blackboard, these slides. And I should be able to put our whiteboard stuff up there as well. So strategy for solving problems. So as you saw, it was easy enough to state Newton's laws. Ooh, we got a question. Yeah, actually, let's take a second. Are there additional questions? The difference between mass and weight. So that's an excellent question. This is a subject that we tend to blur together, right? We talk about mass, how heavy is something, and you may give it in terms of its mass instead of its weight. So mass is the measurement of an object's resistance to being accelerated. It's measured in kilograms. Weight is the force of gravity on an object. And normally that's given at the surface of the Earth. Yeah, excellent. So we get some interaction between folks in the chat. You can distinguish between mass and weight. But that's a good question and a good thing to note. So, in other words, or another thing you can think about with this is you can't change an object's mass, but you can change its weight. So, how might you change an object's weight? Ideas? What do you think? Let me actually. Tell you what, let's jump out of our slideshow and I'll pull up the whiteboard and we can talk about this. So we can come back to our problem solving strategies once we've talked about a few of these details. Yeah, exactly. So you could change the acceleration due to gravity. So, okay. So let's see. Mass is not the same thing as weight. Mass is a measurement of an object's inertia. Okay. In Newton's second law, weight is just the force of gravity on an object. So weight, a lot of times we would we'll say F sub g for force of gravity, and this is given by an m given by mg. Yeah, so now technically this is a vector, right? It would be pointing down. We're being sort of fast and loose with our conventions here, but normally g would be negative. So why don't we just say that the weight, the size of the weight, the magnitude of the weight is mg. Ah, buoyancy. Buoyancy is more complicated. Yeah, so this you can't really change. without changing the object. This, however, if you change g, the weight changes. So, in other words, a good example to have in the back of your mind is think of the moon. Of moonwalks. You've seen those videos of shoot of astronauts bouncing around, bounding around on the moon. In that case, since the moon has a lot smaller mass, the force of gravity between the moon and the astronauts is a lot smaller. Uh, in other words, and so the weight on the moon is a lot smaller than the weight on Earth. Um, but the amount of mass in those astronauts didn't change just because they're on the Earth. Okay, I think I'm kind of beating that subject to death. Are there other questions? Yeah, so we're not going to talk about buoyancy at this point, but you guys can talk about that in the chat if you want. Uh, Other questions in along those lines, weight, etc. Let me show you again our checklist. So I think one thing that you will find is that there are just tons of hints and like do this and do that and do the other thing. So I don't want you to think of this as being like the be all and end all strategy for solving problems, but it gives you kind of a sense of how we approach these. So for one thing, I want to emphasize drawing a picture. So you saw how that was useful for figuring out the direction and sign of vectors when we talked about this yesterday. In regards to finding the net forces on an object, this is known as drawing a, quote, free body diagram. So think of that as you find you draw a picture of the object in isolation from everything else. You draw all the forces on it, and then that is an aid to figuring out mathematically what the net force is on that object. So it's sort of a tool for helping us to account for all the forces and their directions and stuff on an object. And like I emphasized yesterday, it's difficult to be quantitative with your picture of the forces or of vectors, right? Especially if they're, you end up dealing with small angles or large and small forces at the same time. It's just impossible to be quantitative about it, but it's extremely helpful for helping you to keep track of which forces are which and which directions they're pointing and stuff like that. So I'll emphasize this while we're solving problems to draw free body diagrams, and I'll give you some examples shortly here. So basically, the game plan is you draw free body diagrams for the object in question. You find the net force on that object based on your sort of accounting of the forces on it. And that will look like we'll add the forces, we'll add those vectors in x and y directions like we did yesterday. And then that'll give us the net force in x and y, i.e. the net force on the object. And then if that object is accelerating, you can find its acceleration, provided you know its mass, via Newton's second law. So if you know the net force and you know the mass, you know the acceleration. That's the game with a lot of problems. You find the net force and then you find the acceleration. Now, if the situation is static, in other words, if it's not accelerating, you find a lot of times you'll be asked to find some missing thing, like what angle is a force at, or what is the magnitude of a force, etc., on the object, so that the sum of the forces equals zero. I.e., this amounts to, or this kind of problem is often you're doing algebra to figure out, you sum the forces in x and you sum the forces in y, and you see some you do some algebra between those two equations that you have for each, and then that allows you to figure out some missing quantity, like a magnitude of a force or an angle or something like that. So that's an outline of kind of the skills that we want to work on. It's telling you this is not as valuable as us looking at some examples. So we're about to do that. Are there kind of questions? Is this familiar? How many guys, or have you seen this before? Give me some feedback in the chat, and we'll. Also, if you have any questions, this would be a good point for questions on this stuff, and then we can proceed. Yeah, I don't expect everybody to have seen this. It's only gonna, only if you've had physics before are you gonna have seen this. It's totally fine if you haven't. We'll try and give everybody a good foundation. So I'll work out some examples. We'll start very simple and build up from there. So my apologies if you've seen this and it's very familiar and it's very fresh. The things that we'll look at to begin with will probably seem really simple, but we want to make sure that we have a good foundation and that everybody is kind of is doing okay and is on the same page. Okay. Like I said, I'll put these slides up so you can refer to them too if you want. So let's see here. Let's look at some examples. Okay. So probably the most immediate example is, and especially when we're talking about Newton's third law, I think that can be kind of confusing. So let's actually start with that. This will give us an excuse to talk a little more about weight as well. So the situation that I want you to think about is you have an object that's resting like on a table. Okay. So this could be, a coffee cup. I have a coffee cup that's sitting on the table next to me. And we already discussed that would be acting on this object. So let's look at this. Let's talk about a coffee cup. So we have the cup, and we have this is on a table or something. You would have the force of gravity that's pointing down, and give that by mg. And you know that this would be negative because it's pointing down. Okay. So that brings up something that can be kind of a consistent source of confusion, and that is if you should include a negative sign or not with your g. I think you should do whatever makes the most sense for you, and you should just be consistent about it. So I'm going to put the negative sign in, and I will try and be consistent about that. It's pointing down. It's negative. Okay. But it also gives us a chance to reemphasize this fact that drawing your picture helps you keep straight which direction is which. Okay. Okay. So the other force that we need in this situation, so Newton's third law, the coffee cup is exerting a force on the table of magnitude mg. The table is going to exert a force on the coffee cup that's going to have the same size, but it's in the opposite direction. And that is called the normal force. So that's normal, meaning, or why it's called normal is just because it's perpendicular to the surface. Okay. And this is an example of and actually, you know, this cup, it's exerting that force on the table, and the table is pushing back. Okay. Okay. So there's a couple of different points that we can make about this. One is that this is an example of Newton's third law. There's an action force on the table and a reaction by the cup, and a reaction force on the cup from the table, the normal force. The other way that we can look at this is in terms of Newton's second law. So if we sum the forces, and we'll become better about keeping our coordinate system in here. If we sum the forces in the y direction, this will give us an example here. We're going to have the normal force. So this is on the cup. We're going to have the normal force. It's positive. We're going to have the force of gravity that's pointing down. That's negative. And what are these going to have to sum to? What do you think? This is going to have to sum to 0 because this thing is at rest. Yeah. Okay. So this is basically the simplest possible example for application of Newton's third law and second law. Now, let's make this slightly more complicated. Let's add some numbers. So let me see here. Okay, I can just scroll down. Oh, and I should mention, or I didn't mention, this mg, right? This is the weight. We already talked about that, but that's just mg is the object's weight, the force of gravity on an object. So just to re-emphasize that. Okay, so let's look at some actual numbers here. Let's suppose that we just had an object, the mass of which is 20 kilograms. We know we have the mg for that object, its weight, and then we would have the normal force pointing up. And we wanted to calculate this weight, it would be the object's mass times g, 9.8 meters per second squared, and that would equal 196 newtons. So, and our unit is newtons, and what direction would this be? What unit vector would you use? Yeah, so we would talk about this as being in the negative y direction. So you can think of that as being the negative j hat. Okay. Negative j hat direction. Yeah, so this gets at, again, this issue I was talking about with the sign, right? I put this as negative j hat because I recognize that it's pointing down. Equivalently, we could have this negative sign here. We could say this is negative mg. We would get negative 196 newtons, and that would be in the j hat. It's the same thing. I just want to emphasize giving yourself a picture so that you can keep that straight. You can imagine, or it may seem sort of trivial to be hounding you on that with this, but as things get more complicated, that picture can really help you keep straight what's what. Okay. So there's a question about the forces in X also zero. That's a good question. There are no forces in X. So in this situation and the example that we talked about above with the coffee cup, the sum of the forces in X is zero because there are no forces. In this situation, the sum of the forces in Y is also equal to zero, but that's because the object is at rest. Those forces are still the normal force minus the weight equaling zero. So in other words, the normal force is mg. So the normal force has the same exact size as the object's weight, but it is positive. So the normal force is in the j hat direction, and this would be 196 newtons j hat. Okay. So kind of building this up from the really basic example, let's make this a little more complicated. So the next thing that we can do to add to this is, let's take our object. So let's say this one is still 20 kilograms. But now let's add an object on top of it. And let's say that that object has a mass of 10 kilograms. So how do we want to go about this? So its force would be 196 newtons if it was falling at constant velocity and acceleration. So if it was allowed to fall, if we removed the table, it would experience a force of gravity of its weight. Yep. 196 newtons. And that would, in that case, cause an acceleration. So that's a good question. And it would be accelerating, so the velocity would not be constant. It would be speeding up. Yeah, that's a good question. Other questions? Well, let's continue with this example. I'm sure we'll get some more questions and we can kind of fold them in as we go. So in this situation, now we have two objects. What you want to do, make a free body diagram for each object. So and maybe we should label, well, I'll just label these. One, you can see what's going on here, but so for object one, what forces are we going to have acting on that? We will have its weight, mg, and then there is going to be its equal and opposite normal force. It's pointing up. So if this object, let's sum the forces again. We'll be real methodical about it. The sum of the forces in x is 0 because there are no forces in x. The sum of the forces in y, we're going to have, like we had before, the normal force minus the force of gravity minus the object's weight. Those are going to sum to 0 because it's at rest. And in other words, the normal force in this case is going to be mg. It's going to be 10 times 9.8, so it would be 98 newtons. Okay. And then for the other object, it's slightly more complicated. We're going to have this object's weight. We're going to have the normal force due to the table. But we're also going to have exerted on this object the mg from above. So let me distinguish these as object 1 and object 2. How about mass 1s and mass 2? So let me just annotate this here. Okay. Let's see. Questions. Will the normal force on object 1 be from the object 2 or from the table? So for object 1, the normal force is from object 2. It's object 2 that's pushing back on it. It's the force from 2 on 1. Try and put that here. And then in this situation, it's the table on 2. One thing that this makes me think about is you can add very descriptive subscripts to your variables. I think this is a good practice to help kind of account for things, keep track of things. So I would encourage you to do that. I should use what's useful for you. I know different folks have different, maybe have used different things in the past. Stick with what makes sense to you. I will try and model that practice, but you don't have to use the subscripts that I use. Okay, so let's look at this this second object. So the sum of forces in x is 0 as well, just because there's no forces. And then in y, we're going to have, the normal force. Whoa, one note. We would have the normal force pointing up, so that'll be positive. And then what else are we going to have? We're going to have the object's weight pointing down. And we're also going to have the force of gravity from the first object onto the second object. So we would also have this. And these are going to sum to 0, again, because the thing is at rest. Now notice when we solve for the normal force, and I'll just add here on 2. What is it? It's going to be m2 g plus m1 g, or we could factor out this common factor of g. And it's bigger. And this intuitively makes sense to us that the table is going to have to respond with a bigger force to keep a bigger force than just the larger block's mass, because it needs to keep the whole thing from accelerating. So in this case, the point, or why I am showing you this, is because, and here, let me put this in a different color. Or here, let me just, oh, and numerically, that would be, this is 9.8 times 20 plus 10, so 9.8 times 30. It's about 300 newtons. Okay. Let's see. Where is the sum of Fy notation? I don't follow that question. Okay, so what I wanted to emphasize, let me put this in a different color. So important note, This is an example of the fact that the weight is not always equal to the normal force. Let me see. Just to clarify, the object's weight. So this is an example where the object's weight does not equal the normal force. Sometimes we can get kind of second line. Sum of sub f sub y is used. Where is the sum of fy? Sorry, I don't understand the question. So just to emphasize, let me give you an example where this is I think what you're talking about here, I've solved this for Fn. So this is Fn, and then I'm saying, hey, Fn is equal to these things. I subtract them over, they become positive. Okay. So let me give you another example of this where, so this is an example where the normal force was larger than the block's weight. It's larger than object 2's weight, but it can also be smaller. So let me show you that. And the kind of situation, I'll just draw a cartoon of it, that would get at that would be this one. So suppose you have some contraption where we still have our block that's 20 kilograms, but now we have like some pulleys or something. Now, the free body diagrams for this, I'll add them on, I'll draw the forces in a different color on top of here. How about? So we would have, just to use the same convention that we were using before, we would have M2G that's pointed down. We would have the normal force that's pointed up. But now, instead of the weight of object 1 pushing down on object 2, it's up. So, and a lot of times we use the letter T to denote this as tension. Okay. And then on this we would have M1G, the force of gravity pointing down, and then that tension pointing back the other direction. So in this case, if we look at object 1, or sorry, object 2, notice if we sum the forces in y, we're going to have, well, let me just, we'll do object 1 real quick first. If we sum the forces in y, we see that we would have tension minus M1G equals 0. They're not moving. So in other words, the tension is M1G. Now, if we look at object 2, what do we have? We're going to have the normal force pointing up minus M2G pointing down. But now the tension is positive. And that's going to equal 0. So if we sum this, or solve this rather for the normal force, and just to clarify, on 2, we would have M2G minus tension. But our tension is equal to this up here, so we can substitute that in. So in other words, in this situation, it's the weight of object 2 minus the weight of object 1. So this is another example where the normal force is not equal to object's weight. Okay. Okay. That's a pretty reasonable stopping point. So questions. What questions do you have? So these are sort of, we're working with these definitions, getting up to speed. Maybe let me just list on here kind of to recap. See if this sparks any questions. So we've looked at Newton's three laws. We haven't really used them a whole lot yet, but we're starting to build up some definitions for things like force. We talked about a couple special forces, including the weight, an object's weight, as well as the normal force. What else? We looked at how this normal force is not necessarily equal to the object's weight, depending on the circumstances, and kind of foreshadowing, looking at, thinking about where we're headed. We're going to, of course, look at situations where the forces don't sum to zero, where there's a net force, and in that situation, so when the sum of the, it's not a good sigma. That's not a good sigma. I got to get used to this drawing on the computer. When the sum of the forces does not equal zero, you're going to have an acceleration. And if you know the forces and you know the mass, you can find the acceleration. So that's where we're going. We're going to apply Newton's second law and see how objects accelerate. Questions. What questions do you have? Anything? Pretty basic. It looks like most people have seen this before, but if you haven't, that's totally fine. We'll get everybody up to speed. With regards to lab. So lab, it'll be a meeting in teams. I suspect folks have been, yeah, just for clarification, there aren't any equations per se for Newton's first law. Yeah. The math is really we mostly introduce it with regards to Newton's second law. So lab will be a meeting in teams tomorrow. So it should be in the calendar. Like as far as I understand, you get some sort of notification. I didn't get that straightened out until after our first session was in process. So there are a few students who will likely, I tried to include you in some invitations for the labs tomorrow so you can jump in whenever you want and get up to speed with that MATLAB stuff. Yeah, that said, with regards to lab tomorrow, look at the directions I put on Blackboard to get MATLAB if you don't already have it. Actually, here, I can make a couple notes here. So try and install MATLAB if you don't already have it. And And the other thing is since we never got to meet the Friday session, we'll talk about the free fall lab too. So if you have questions about that, don't sweat it. We'll talk about. Um, I've gotten a number of questions from students, and we'll kind of go through that somewhat together because we weren't able to talk about it. Okay. Other questions? What other questions? So if you don't have any questions, you can feel free to sign off. But if folks have questions, I'm happy to stick around as long as you want. We can talk about stuff. So how does this relate to spring mass systems? So we'll learn later about how a spring exerts a force, the force due to a spring, and the acceleration that that will cause on a mass and how it will move as a result of that. That's called the harmonic oscillator. That's a really fundamental system that we will spend some time with. Other questions? Other questions? Of course, if a question occurs to you later, feel free to post about it on Teams or in the comments, and we will go from there. Other questions? True. Yeah, yeah. Since we're just changing topics, I think once you dig into the homework, I'm sure some questions will arise. I tried to structure that with, there are a few places where the problems are maybe confusing or something, so I put some hints in there to hopefully kind of point you in the right direction. Also, I'd say, if you have questions about stuff that you don't want to talk about with the whole group, shoot me an email or um, there's a, I think there's a message feature through Teams. You could contact me through Teams. We have lots of ways to communicate. So, other questions? All right. I will sign off and we will see you next week or Friday if you have virtual lab tomorrow.